Red looks
All right,
stylish.
here we go.
Okay.
Here we go. Lock and load, kids. Folks, here we go. Bring it in. We're going to make this day count. Thank you. We do. We should be all right.
Because Chloe said to this direction.
Yeah.
Okay. We tell your neighbor?
0. Yeah, 0. Because it's yeah.
Right. So everybody goes. It's perpendicular. Sorry. There's no component of the radius that's perpendicular to the current, or there's no component of the current that's perpendicular to the radius. Into the board, like it turns.
That'd make a field though. So.
That's true. Okay.
Oh no, not this. Deeper down.
Tell your neighbor.
Wait, you guys got? Wait, hold up. Oh, I did left hand rule. Oh.
Okay. Is everybody going in? Okay. That makes sense. Okay. This part here has no influence. Okay. Oh.
Wait, heck, hold on.
How is this tricky?
Because you have more of the stuff.
Oh.
It's just further away. But because you can just do
by what's his rule? The radius doesn't.
Oh, the radius
That is not true.
No, by the. Micah, you're sick. Stop speaking. Child, you're attacking. We're gonna do that one. Yeah. I'm not disagreeing.
No, you said the radius is having an effect.
Have a conversation.
I want to say no. Square the distance. But yeah, the radius didn't matter. You said the radius didn't matter. Oh, Tim, that's smart. I was thinking of Smiley, I'm having trouble with right-hand rule. Like, I'm not kidding. With this one? No. So, I can do that. But when I get to, this part, I have trouble, knowing, because sometimes
So here's a different way to look at it. Think of the tennis ball on a string spinning around. You let go at the point you're trying to evaluate. Which way does the tennis ball fly?
Like the way your fingers are going is the way it's spinning. So it's going that way.
Straighten the thumb.
So spinning like around. Just spinning like that around.
Or not P, it would be coming to me on that
There
one.
it is.
Or in this case, you can. Okay, thank you.
You're welcome.
You gotta have the proper form.
Okay. What do you think?
I think it's A.
I think it's B. No. I know B.
Okay. A. I'm pretty sure is correct. I'm trying to think of definitively why that is. Actually, we're going to prove it here in a second. Yeah, because it's closer.
You'd be doing right-hand rule now. What the heck is C?
Why are you dropping all this stuff and then he's gonna be like, we're just gonna use Ampere's law, and actually they're all the same.
It's got to be that one. Okay, everyone be quiet. I'm trying to right hand my rule.
Yeah, but there's less. He's going. He's in the matrix.
Tell your neighbor.
B and then C and then A. Before changing.
Yeah, because C is closer.
Yeah, that's what I was
So
saying.
it's gonna have a greater. But I also
Hold on.
I know, but it's
still. Oh, wait. Hold on. Because these
Okay,
A is the
page
into page.
C also goes into page.
It's just that one is like
It's just a part of it.
Okay, what do you say?
Just because one square is 5. Because like when it's over the point, it's going like. It's going this way.
I'm gonna say. I want to say it's 5.
Yes.
Okay.
I'll agree.
Here-
Here-
Yes.
Like,
Yeah.
For C though, like when
Okay, it's closer here. Now, here's I've probably rearrange this. Let's calculate the field at point B. So, what we're gonna do? Okay.
It's not that bad.
Okay. So, but watch yourself. So we're using this. Okay. So all this is sort of constant. I mean, it's constant for this part, and then it's constant for this part. These two parts don't matter. Is everybody good? Okay. So when we integrate this, recognize as a half of a circle. Okay. Does that make sense? So when we go to do this, we've got, it's the same current. Going from 0 to pi r. So, thank you. And that's just so pi r. So you end up with 1 over 1 minus 1 over, actually 0.01, 0.02. Good with that? So the closer one's going to have a greater effect. It's going to have a greater magnetic field. You okay with that?
Wait, is this for the bottom circle or the top circle?
Both of them. Sorry, I jumped the gun here. So here's our overall statement. Okay, for a semicircle. Okay, so the inside one is going to have a magnetic field of times 0.01, and this one's going to have the same thing, just 0.02, and we subtract them, and this one's bigger. Okay, good with that. So there's never a point at which you can go out far enough that the length of that compensates for the distance away. Okay, good with that? I should probably put that here. Okay. All right, so yesterday we talked about what happens if we're not at the center of the circle for a loop. I've not seen this yet come up on the AP test, but it isn't beyond your, like, I still, like, okay, so A is the radius. It's kind of a weird notation, but A is the radius of the loop. X is the distance, so we're still along the axle, like the center axle here, and R is this distance from there to there. Okay, so this R, we have the square root of x squared plus a squared, and then we square that, so that gets rid of the square root. Okay, and then we want, so as we're looking at this, we're grabbing hold of this, the magnetic field at that location is going this way. Okay, from this, just the segment here. Okay, the y component gets canceled out from this one. The x component is what we're adding up.
I thought it's all going this way.
So at this location,
It's all going in the X, is what I thought.
Nope.
Oh.
Does that make sense? We're gonna yeah. This is getting pretty deep. Yep. Okay. So the y component gets canceled out with this one, the opposite side. It's just the x component that we're adding up. Okay. So
isn't that is that not Smiley is it, ring of charge?
Yep.
Like, isn't it similar to that?
Yep.
Okay.
Except the direction of the electric field is way easier. It's just straight this way.
Why is it not?
And magnetic field is based upon our right-hand rule.
But like, wouldn't it all be A then, or wouldn't it all be in the X direction because it's like this, right? Like.
So we're not looking at it right here. That would be the case. That would be true if it was right there. It's out here. So it like circulates.
You're just further away.
It's from this point. It's this. That.
Oh, that's so weird. Okay.
Yeah.
But total, it's all in the Y.
Okay. Will you pause
Total, it's all in the X. X being this way. Okay. So the magnetic field does something like this. So we're grabbing hold of this, and it does. So here, like Sammy, you were saying, it's coming out of the page. This is not symmetric. It does a whole loop. And so out here, it's going up to that angle. Okay. This y component of this guy is going to be canceled out by the magnetic field produced by this thing as it comes down. But there's the x component that isn't canceled out, and that's what we're going to add up for the entire ring. So this is what we got to do, the cosine of that. This angle is that angle. Find the cosine of that. Cosine, this is the cosine component based upon this triangle here. Adjacent over hypotenuse. And then combine all that junk together, stick it in your calculator.
Well, I realized that literally nothing's in terms of L, so we can all get back to that. Oh, wait. Yeah.
Okay. So then we integrate.
Question.
Yes, Brad.
Yesterday you said that you couldn't do this. Could you not do Ampere's law for the ring?
Correct. That's what you can't do.
You have to do this.
Yes. For a ring. Mm-hmm.
Okay. So like anywhere along the axis of a ring, you have to do this.
Yep.
That's dumb. But okay, thank you.
Actually, anywhere along any axis. It doesn't have to be along the axis of the ring.
It's simpler along the axis.
Yes.
Yeah, well, they're not gonna probably ask you.
No. This is as deep as you get.
What's special about a ring for Ampere's law that you can't?
Because if you're trying to evaluate a point here, I'll come back to that. That's a good question. There's really no good path to draw an Amperean loop to calculate that. There's no symmetry. That's probably an easy answer.
You can take the contour integral, just so you actually have to take the contour integral.
Okay. All right. So the summary of this, after we get an answer, this is our expression for the strength of the magnetic field along this axis. Well,
Will you go back to the last slide for 1 second? Sorry,
yeah.
I need one more thing. I should probably write this.
It's like, oh, I'll post that on I'll post this PowerPoint on Canvas.
I'll still forget about it.
Okay.
Actually, no, I probably.
I mean the answer is on the next slide.
Okay, I'm good now.
Good.
Yeah, thank you.
Daniel, good. Brad.
I'm just drawing a diagram.
Okay. All right. So this is the answer to all that integration. If you stick it in your TI 80, whatever. So this is what we calculated yesterday. This thing. Okay. This is definitely in the realm of possibilities what you're going to have to calculate on the AP test. I would be shocked if they made you do this. I would say it's well worth skipping that and losing 3 points max. Okay, and maybe just start with this expression and get at least a point.
Except that's a really simple integral because literally nothing's in terms of L, so you're literally just taking everything out of the integral.
Yeah.
That's true. That is a good point. So there's no variable here that's changing. Everything's outside the integral. So you just substitute this into there. Well, okay. And so this is at the center, and as we go off, it yeah. And so fun fact, at one distance radius away, you're actually at half the strength of the magnetic field. That's just a factoid. Like, so out here, where A is equal to X, just stupid fun fact. All right, so this is getting more conceptual. So here we have this is like that disc magnet that you had for the guitar lab. Okay. Out of north into south. Okay. Having a loop of wire with current flowing through it creates the same magnetic field. Okay. It is not. No. I don't know. That's a great question. Depends on how much current you you've allowed it to go through there.
No, he was right. Okay.
Yeah, I don't like to wear the same shirt all day. I get tired.
That's when you just take it off. Cal, go away. We're focusing.
Sam, is that you?
Did you change your head, Sam?
You saw a Dave's email the other day. About the,
Yeah. Yeah.
I got the answer.
You? Okay. For me.
you got a microphone on. I don't know what you're saying. Got somebody I don't know. Maybe.
No, you got you. Yeah.
Oh, I know.
Yeah.
I think I got it.
Both of them.
Oh, you got more than one?
I have to look at. Like
I heard
one.
one of them.
One's
Yeah. Okay.
yeah.
We can
Semesters.
talk later.
Yes. Okay. Everybody got something? Okay. North Pole going down. Okay. Good with that?
On the bottom.
Yep. B. So this is the magnetic dipole, or what was that term?
Oh, I like this one.
Oh, wait a minute. No. There. Okay. Whew. So you stick your thumb points the direction of the North Pole.
So the dots refer to the magnetic field at that point?
The current.
So the current's going this way?
Current's going into the board here and out of the board here. So this is the alternative right-hand rule.
Oh.
Good with that? Okay.
For extra effect, you have to put your hand. That's what they call. Oh, and then this can be your little electron.
Okay.
What? Oh, what's the? Okay, so. Should be. Oh. Okay.
Repel. Oh, that's stupid.
Right.
So one or the other.
I thought it was representing like the direction of the field.
Oh. Tell your neighbor. Correct answer is B. Good job. Okay. You want the field going this way is the North Pole. Okay.
I think this is a pretty easy quiz. I'm gonna be honest.
We've answered this question like 7 times.
This is true.
Right-hand rule.
Just-
Yeah, I think I would say.
I don't understand why it is anymore, just I know that we've answered this so much.
I'm a big fan of the loops that have current just going around forever.
How does that happen?
Superconductors.
Superconductor, yeah, zero resistance.
You get it going and then you just. I don't like school water at all.
Me
Me neither.
What? I need more.
Damn over here. Love school water.
Going over here.
Stuff is here.
Let it run for a while.
Powell has me do this.
Why does that
Because he doesn't let me leave the room because it takes too long.
The water's been sitting
No,
a
it's
while.
worse.
It is the same water. It's just been sitting. Like when you like
You've also explained this.
when you hook up your hose, like now when it's like not gonna freeze anymore, you're not gonna drink out of the hose right away. No, it's just
It's like the
junk.
wire that comes with electrons.
Okay. Is everybody good with the traction?
You can have the wet water.
Okay. So, Ampere's law.
Sam, did you get any extra wet water?
You probably turn off the water. Okay,
It'll get some
Ready?
right out. Yeah, they build a features
Smells
of
like
water.
tap water.
I think that you're taking a shower with that thing in there every morning.
My tap water is so much.
Why? That is like a horrible spot to take a shower.
Okay,
That is true, right?
so here we go.
This is low water. That's
This is analogous to Gauss's law. Now, what you're going for, if you can, you want to draw a circle. Okay, so that the path, what you're trying to do is this. Do it so you're drawing a path so that the magnetic field is constant. So this is just 2 pi r. That's the circumference of the path taken. That's kind of what you're shooting for. It's not an always, but
explain that again?
yep.
Oh, as in like our Gaussian surface, but our Amperian
Yep.
surface.
The Amperian loop is the.
So like a loop of magnetic field, you mean?
Yeah, you want to, the path that you're evaluating, you want
So that
part of that path to be where you're trying to evaluate the strength of magnetic field. So with Gauss's law, we would do this. Here's a point, and we draw a sphere, and we would do this, and we draw this as a sphere, and this would be surface area, 4 pi r squared. Right? Does that make sense? And then that was charged enclosed over epsilon naught. Okay? Good with that?
What does oh, never mind. I was gonna ask what does I included mean, but I know it.
Okay. So
It's like
similar, definitely similar tricks, techniques. Yeah. Good with that?
How do you just like draw whatever you want? Like how do you know that?
It's like Gauss.
Okay. So it's a dot product. So we're doing a line integral of a dot product. No, yes, you do. Yes, you do. Yes, you do. Okay. A dot product, you're finding the component. Every time you do a dot product, you're finding the component of one of the vectors that is parallel to the other vector. That's what we like with work. Work is force dot d. It's finding the component of the force that's parallel to the direction of motion.
So we are multiplying.
So
It works. The thing that is parallel. No,
okay.
Smiley, I really do not like the fact that magnets.
So it's
that breaks my brain.
Is it
They can, just not.
Oh, but it
particle.
doesn't matter if you do force parallel to distance or distance parallel to force.
Right.
You just okay.
Correct.
I'm
Now,
struggling with that for some reason.
okay. So what we're doing
Um,
is this is taking that concept and applying it to calculus, where if the path that we're taking is wacky, if the magnetic field is perpendicular to that path at all points, then you have zero. Then this integral is equal to zero. This path integral is equal to zero. Okay. So Emma, to touch at your question, how do we know? If we have a field that looks like this, and we're like, I'm going to draw this path so that it's always perpendicular, then I know that this line integral is equal to zero. Okay.
Parallel or perpendicular?
Dot product finds the parallel component. This is oh. Okay. Dot product finds parallel. we're we're doing the integral of the dot product. The dot product is what's parallel. Doing cross product is perpendicular. Dot product is parallel. We're just adding a second step of finding the integral, adding all those up.
Except the cross product gives you a vector.
Yes, it does.
So, moving on to the next slide.
Okay, so
You don't have to draw a circle, you can just draw a line.
you could. Okay, you'll see. They'll give you special examples. You don't have the math to be able to do this, but this is the idea. So here, if you knew that the magnetic field was doing this, you would draw the line so that this would be equal to the length of that line times the magnetic. To do Ampere's law, it needs to be closed. Okay.
Whoa. Oh, I'm understanding what's going on in this picture now.
That makes sense?
Okay, can I draw the picture really quick?
Sure, Daniel.
Or I might have just asked, but how do we find the length of such a weird line?
Oh, she didn't ask that question, and you would need the function of that to be able to integrate that.
You remember when we did length, arc length?
You good with that?
Wait.
You're not going to have to do that math. Okay. All right. So the instead of with Gauss's law, the most simple thing, the simplest example was a point charge. Okay, and then we did the Gaussian surface a certain distance away. Okay, we drew a Gaussian surface, and we say the electric field, the area, when we added that up, turned out, so you have charge enclosed over epsilon naught. This becomes 4 pi r squared over q enclosed epsilon naught, and so you find the electric field to be 1 over 4 pi epsilon naught times charge over r squared, which is just k q r squared. The electric field of a point charge. That was the most basic fundamental, like Gauss's law applied to a point charge.
Is it bad that is like just not clicking in my brain?
There's worse scenarios.
Okay.
Okay.
Okay, that actually that's sick.
Okay.
What about Ampere's law for point currents?
This is going to be our simplest, most foundational example for Ampere's law. We have a single current, it's constant going through here. We're going to integrate. Here's our Amperian loop. Okay, the magnetic field is always tangent to this thing, to that path, the Amperian loop. So we get and so that's enclosed. You can read that on there. Can't. That's a dot. Okay, so I'm looking for that. The integral of this distance, you're just pretty much adding up this distance, and that's 2 pi r is equal to mu naught. So you find the magnetic field is equal to mu naught over I n 2 pi r, and that
would that be like if it's a wire and a giant circle?
It's the current included in going through. That's probably a better.
So like 5 amperes or whatever it is.
That's a better preposition is through.
Yeah.
You all right with that?
Yeah.
Okay. Good there. And this is what we got. Did I even say that? Oh, boo. Too far. Did we get that already? I think we added that up. Right there.
Oh yeah.
Can't even read it. This right, boom. That. That is that.
If you could pass through the previous slide on your way back, that'd be nice.
Which one? That one?
This? No, keep going. Like old.
Like the one before the one.
The one before the one. The one before the one we just did. With the that one. Cool.
Yeah.
Thanks.
We had the same thing with.
Okay.
Okay.
Is everybody good?
Yeah.
That's our starting point. Okay. And I talked you through all that. Okay. Okay.
This is not bad.
No, this is awful.
There's just 3 eyes going through it.
No, but then
Right.
there's one that goes the other way.
So here for direction, you need to specify the direction of which way you're traversing along this Amperian loop. Okay, I'm saying I'm picking this way to be sorry, not positive. This is the way that I'm evaluating this loop. So you use your right hand rule again and put your fingers in the direction that you're evaluating this loop. Your thumb defines the positive direction of current. So anything that's going this way, I2 and I4 have positive current. This I3 has negative current. And therefore, like when you're adding up all of the magnetic fields, these are positive values, and this is negative values for the current going through it. Daniel, you good?
Since technically these currents are perpendicular.
No, because the magnetic field is the magnetic field is what we're evaluating, not the current. You all right with that?
Oh, okay, yeah.
Okay, it's a good question. How are we
Can you
doing?
repeat the question?
I wouldn't worry about it.
Got it. Okay.
Yeah.
I was not.
So where does this give us the magnetic field? Like what?
Great question.
On the graph, where
Along this line.
along the line. Okay.
Well, yeah, for this, it's going to give you a function because it's not constant.
Somewhere it's gonna be different along
But
the graph, right?
you could solve for the magnetic field.
At that point. Okay.
But it'll give for this, it would, like, if you had the math ability, it would give you a function.
You don't have to stay on the same consistent thing.
Right.
You can take whatever loop you want and just
Right.
make yourself that annoying contour.
Okay.
That's why we know center things. We put it in the center of the circle if we can. That way it's consistent. Okay.
Yep.
Actually, you just want something where the magnetic field is constantly perpendicular or constantly parallel to your loop.
Yeah.
Then you just need to lengthen your loop. That's why we like circles.
So this is more conceptual. This isn't like you don't have to do crazy math.
I like that.
Yeah. It's like gas. You're adding charges.
Yep. It's been net.
Tell your neighbor.
1, 2.
Okay, so we want that to go opposite. This is positive direction of current. This needs to be negative to make the total 7. So into the page. Sorry. Yeah, into the page. Okay.
Yeah. Well, yeah. Hey, gets me to a
Tell your neighbor.
B.
Good. B is the correct answer. Okay. You've got this is positive, negative.
It actually didn't start hurting until yeah, so I basically just like dropped it. But I finished it and didn't like for I was thinking of it and then yeah. So now that actually hurts around my
I'm gonna say I played video games every day.
Tell your neighbor.
B. Yeah.
Bradley, are we bringing
Correct answer is B. There's nothing in here. And these C, the teal, has both of those.
It's
we gotta get the whole physics floors. Okay.
Here we go. Ready?
Yeah.
Is everybody good?
Yes.
Okay.
what the heck is that loop?
That doesn't make sense.
My brain went through, whose name could I say in this class? And Deez was the only person that worked.
The funny thing is, you don't understand.
I feel like I could draw a loop much better than that.
What?
Oh.
Okay. Correct answer is A, into the page. Is everybody good? Okay.
You too.
We draw these in America.
Oh, I just
American. Oh, why would you draw that?
Just
If you wanted to be a
yeah, who wants to impose this kind of terror upon us? Which way the clock goes that way. I'm so lucky that I have a clock on the AP test. Because I still don't know counterclock.
I just picture a clock.
and then I get it wrong.
Okay, I can do that now that I know which way it is, but I don't think I can do it all slap, to be honest.
Thank goodness this is a second hand, otherwise you have to wait a full minute for What do you do?
I like blink and have to wait another minute.
You could just look at the numbers and like, hey, this sequentially gets bigger.
No, but
When I go from 12 to 1, it gets smaller. I don't know.
this is why you use a 24-hour clock. That way, it's when it goes from 23 to 0.
Yeah, that way you use a digital clock.
Now you don't know which way clockwise.
Which way does a digital clock go? Clockwise or
My digital
I'm
clock
almost
goes
there.
up.
You know what's at the minute?
don't know what the point of the loop is cross hatched.
It's gray.
Okay. I can see that.
I don't. Yeah, whatever. Okay. We're almost there, kids. We're on 40. We need 43 minimum.
Okay, we got this.
Okay, correct answer is? Good, 3. Okay.
Jay. What is that?
Current density. Okay, so this is a wire. We're looking at the cross section of a wire. There's current flowing through it going into the page. It's saying that the current density is uniform, meaning the current divided by the area.
Why would the
Okay. They wanted how much current is going through here? Sorry, how much current is going through this section of the whole thing is constant.
This whole circle's
Whole yes, this thing's a what? Think of a hose. Think of a hose with water flowing through it. I want to know how much water is flowing through this section. That portion of the wire into the wire.
Okay. It's current it's evenly distributed throughout the line.
Yes.
What the heck?
Yep.
I got my answer.
No.
Hence why I wanted to get to this slide. Okay. So we know that this is I'm going to just make that for the portion that's on the inside.
Everything in my body is hurting. Sam, when you do it,
otherwise you won't be able to run for the Pete's nuts.
Pete's nuts. What?
His track relay name.
Okay. Is everybody good with B?
Track relay that everyone did.
It's gonna be so bad.
So I'm just setting up a ratio here.
It's so bad that I'm the fastest one.
Sam's running anchor.
Good?
800.
Okay. So
Can you go back? 'Cause I don't think that was any. I don't think what you got was any of the answers.
No. I'm not fast at anything like that. I'm like bottom.
Oh, because I messed up.
Oh, okay. Yeah.
Now bring that over. That goes here.
Okay.
Good catch. Good catch. Okay. So if yep.
We're gonna have to.
Okay. So here
Because it's outside the same thing.
so I want this that's through. Okay. This is just this. It's just like when we're doing static electricity, and it's like inside the ball or inside the cylinder of charge. Okay. So this is 2 pi r equals that over all that junk. Is everybody all right with that? Okay, because our Amperian loop is this inside there. And so that knocks out one of those. And so we get okay. And so we find that it's linearly proportionate to the distance from the center, and then once it gets on the outside of that, it does just a normal 1 over r, proportional 1 over r, and this is directly proportionate. Good with that? And so the foreshadowing has now been revealed as what happens when
Oh, yeah.
that's not constant. Okay. I mean, that's how I think it works.
Yeah, no, you generally like to have constant current.
Yeah.
Oh, because the wire has internal resistance. Oh.
Well, that and just the electric field generated isn't constant. Okay, so
I'm on my phone now. Am I gonna pay attention?
yep. So that's current over area. Yeah.
Will you go back a couple slides and explain something to me?
Yeah, hold on.
Could you go through the whole thing again?
I listened to you, but I wasn't paying attention.
Can you tell me the meaning of why?
Can you explain what a charge particle is?
Whoa, Sam!
What's up?
You didn't tell me you were nominated for Indiana Academic All-Star?
That was the thing from a while ago.
Oh,
What's that?
that's a C.
Nice.
That is an F.
That's not an F.
I'll hit it harder.
No, don't hit it.
Do it again.